Thank you for introduction. Let me changing the subtitle a little bit. Today I'm talking about mainly fabrication, not animation. This is my self-introduction. I'm from Autodesk Research that is in Toronto, Canada. And my research interest is mainly real-time simulation during interactive design to facilitate physical creation. And I did a couple of research with this context, and then I'm briefly going over this research. And here is introduction. And there is amazing artist created fabulous pictures like this with oil painting. And recently, the medium is changes, and people began to create something with a digital medium like this. What's in the as discussed in morning session, it's very good because there is an editing like undo comparing to physical medium. And what I think it's the same impact as computer graphics in some display is 3D printing. So 3D printing is around for 20 or 30 years, but recently it gets very popular among ordinary people, and many people are playing with it. And what's very special is about 3D printing is it's 3D digital, so people can share and mash up what they find online, and they can also like publish their own like designs freely. And what's a 3D medium like 3D printed plastic is special is it can create functional things. So instead of like a picture that hanging in the wall or some sculpture putting on the desk, people can create some artistic stuff that is also functional. For example, this kind of violin and clothing and furniture and airplanes. And these are good, but the design of these functional stuff is difficult because we have to take care of physics while designing these kind of things like sound physics, deformation, fracture, and aerodynamics. Traditional design workflow for such kind of a functional object is use of design tool as a CAD system and simulation tool as a CAE system. What's typically bad is there is a gap in between, so people cannot, it's very difficult to bring what they design to simulate. And also, it's, people have no like intuition how to interpret simulation to improve design. And so what I think is essential is interaction between design and simulation. And I recently find this intuition because I happened to bought 200 CDs very cheaply sold on Craigslist. But I didn't, what I didn't think about is how to store it when I bought this one, used CDs. And I don't like, I care like pre-made ordinary furniture. So what I try to do is using some kind of some toy called Kennex to build some shelf that can accommodate 200 CDs. And that was very tough because this is essentially toy and does not supposed to support this kind of heavy object. And I did a lot of like play with physics. Like sometimes it's topo, it's sometimes deformed. And I got impression, truss structure, like Eiffel Tower. And then with this inspiration, I could build this furniture, like the furniture that have triangle element inside, and I could store some CDs. So the important lesson here is we need to tightly integrate design and simulation. We need to play around design and what happens in physical world to get a nice functional shape with some originality. And with this context, I have research about furniture design, and what this research goal is some furniture design interface that allow non-expert user to design kind of non-ordinary eccentric furnitures. And the challenge is that when we build furniture, it should be functional. The functional furniture, I mean, is it should hold weight, and it should not topple. And so to design this kind of functional stuff, I incorporate design and simulation interactively. So there is a design space of furniture in this two-dimensional illustration. So some kind of furniture is valid and some of are invalid. And user can play play around this design space and instantly have a feedback whether it's invalid. And if it end up in invalid design, user can get back quickly with guidance to maintain this validity. So what's the guidance? Here, I in this system provide guidance that shows a range of editing and also a suggestion if the design is invalidated. So let me show a live demo of this furniture design system. And so this is a furniture design space, and user can draw shape like Google SketchUp. Then the nail joint is added automatically. And user can also put the weight on the top of it. Okay, and also user can edit the shape. So far, this is same as ordinary geometrical editing, but what is different is it have a simulation tightly integrated into design. Let me launch again. So here, structure says OK, but if I try to edit this design parameter, there is an arrow pop up. This arrow shows how much design can be still valid. So if I exceed this valid, there is an invalid nail joint showing that, and this means this furniture can be collapsed. And also, if I make it, sorry. If I make a furniture like this, it's say it's not stable and showing direction, it will collapse. And it will guide the user into valid design by suggestion. So here is a suggestion interface. So there is 6 different suggestions that can be fixed this toppling design. And user can choose whatever they want, and user can continue working on this valid furniture. So if it is invalid, it shows suggestion, and the user can get back. And this is a little bit more complex example with table. And I want to make this table a little bit smaller, but in some extent, there is some not durable nail joint, and I can continue editing by choosing some valid design. Not durable, and then there is some other design, and user can, without thinking, can make something valid, well, satisfies their user's intent. So instead of the system just simulated, it's also responsible to get suggestions to guide users into valid furniture design. And another example of integration of design and simulation is musical instrument design. So motivation is musicians also usually want to express themselves with also shape with musical instrument, but acoustic musical instrument especially is usually boring. For example, this metallophone, it's always some array of rectangular bar. But if we couple the design and simulation, we can make a lot of more interesting metallophone. So here, the left window shows a metallophone design, and right window shows eigenmode analysis that predicts the tone of this metallophone. And while the user edits the design, there is interactive feedback of this simulation to guide user into design of right tone. And with this software, user can satisfy this very difficult value constraint while putting some aesthetic aspect in the design. So we gave this software to artists, and here is what we got after 5 hours of creation. So as you can see, this design is very difficult with traditional separated design and simulation system because each metallophone pieces satisfy some constraint that eigenfrequency is some with musical note, and also like artists have to take care of overall fish design. And here we show the difference with previous approach. In the typical CAD and CA system, the user get back and forth between design and simulation. It's like exchanging surface mail between user and simulation computer. But our approach is that simulation is happen during the design. It's like talking with a computer online. So it's more easy to make something functional. So the challenge of this simulation and design integration is it's very difficult to achieve this speed during design change. There is a lot of research about simulation, real-time simulation response with respect to external force. But very few research have done that give simulation feedback during a design change when I start this research. And while I'm doing this kind of research for several years, we have three techniques that is shown that is targeting this physics behavior. For deformation, we find out sensitivity analysis is efficient, and for fracture, we find out cross-sectional analysis is efficient, and for aerodynamics, we find out that data-driven analysis is very good. And I will go over this one by one. So first, interactive deformation design using sensitivity analysis. And so motivation is fashion design. So the clothing you wear is made out from two-dimensional fabric. It's also like cut out such a way that fit into the three-dimensional human body. Because this two-dimensional clothing cutting pattern and the 3D geometry that is on the human body, there is no obvious connection in between. So it's very difficult to design a new garment. The artists have to go back and forth between pattern design and putting on the mannequin to try to see how it deforms. And we made software to greatly make it easy with tight integration of simulation and design. And I will do live demonstration here. So here is our design system. And the left window shows a closing pattern, and right window shows a simulation result. And there is a real-time closing simulation in the field of computer graphics, well studied. But what is not there is a pattern design system. So if we try to design a nice pattern for him, we have to go back and forth between the pattern editing and physics simulation, and have to go back and forth a lot of time. What we achieve is a real-time integration of 2D design and the 3D simulation result here. And let me show here with this armadillo closing design. So here, first we notice this tail is poking out from this clothing. It's very uncomfortable for him. So we will shorten this clothing to resolve this conflict. And also, at the side, it's not covered, so we will make it longer. And also, this neck part is not covered, so probably it's not so warm. We will change the simulation, but here it doesn't change, so we change here instead. And we have a covered neck. Okay. Oh, it's flickering. Okay. And probably I run more simulation again. And the abdomen part is not tightly fitted. So let me cut dart. That is a small hole to make this clothing tight. So here, I drag, adjust the size of this dart so that I can see how it is fitted onto this geometry. And I can adjust the position and also size. And it's poking again. Okay. And okay, its neck is covered. Okay, here we go. We have clothing for armadillo. Okay, let's back to the slide. So the basic idea to integrate the design and the simulation result is sensitivity analysis. So here we assume that the clothing is static and have a one-to-one mapping to the clothing pattern. And we change mouse position. There is only one solution, static clothing deformation solution. And we can write it as a function. What we do is taking differentiation of this deformation with respect to mouse position. So we have a deformation pattern when mouse is moved x direction and y direction. And with this linear combination, we can well approximate the deformation. And we can start the simulation here, real-time simulation here from this warm guess. So this is an idea how to achieve this real-time integration of the simulation and design. And here is the result. We try to make actual wearable dresses. Okay. And then let me move on to strong 3D, interactive strong 3D shape design by cross-sectional structure analysis. So the key, so the motivation here is if when user design some 3D shape, user tend to design weak structure. So this is an example of 3D print some user put on the line. And while after 3D printing for hours, it turned out to be failure, like this. So our goal is real-time weakness detection. If user design this kind of weak shape, the computer tell which part is fragile. And then user thicken this design. And computer interactively say, here we go, and we can print with confidence. And here is what we have. So the colored some lines show the weak part of this 3D model. And user attach this ear and topology changes and the weak region are automatically updated. And this can be very high resolution, like 600 kilo triangle. And also with this crazy resolution, there is interactive feedback of simulation result with about how strong this object is. Let me show the live demo. Actually, this system is taken into a software called Autodesk Mesh Mixer, and we can everybody can play it around. It's a free software. So here is an object we want to print out, and user just hit the strengthness. And then there is some weakness map the system shows. And if it is weak, user just inflate this part slightly. And then user can see how it weak, and it's there is no weakness here, so we can print out this object. There is another weakness, but we don't care here. And also, this new cross-sectional analysis is very robust to the geometrical deficiency of the 3D model. And even if there is a like hole like this, we can analyze strengthness without difficulty. So if we click, yeah, it shows where is a weak cross sections, weak part. And what's more, if we user click some of the cross section, it shows where is the weakest fourth location. So this, if I click this one, this position is a position that probably break this cross section. And the user can interactively fix this problem by looking at this problem. So related work is a structural analysis, and there is a lot of work about analyzing structure strengthness of 3D object. But all previous work was done by finite element method. And drawback of finite element method is it's very slow and it's impossible to achieve real-time response from simulation while editing the design. We have to construct mesh, and also we have to solve huge linear matrix. And FEM requires a fair mesh without hole or intersection, and we need a well-shaped triangle too. Our solution is a new stress analysis technique called cross-section analysis. And it's based on bending momentum conservation. So if I want to know the stress around this middle part, when the force is applied here, I will take a cross-section in the middle. And then I compute a bending momentum act in this cross-section. By definition, the bending momentum should be conserved. So if there is a bending momentum from this momentum arm and force, there should be counteracting bending momentum that cancel each other. And this bending momentum comes from stress inside the object. And we can get the stress here. So how we compute this stress from bending momentum is the assumption that structure will break slender parts and also structure break with bending. And it's going to question how beam bends. And there is a very nice formulation called Bernoulli assumption about what the stress will be when the momentum is applied. Actually, this Euler-Bernoulli assumption is used to design Eiffel Tower. Euler, the genius mathematics guy, create this theory, and then it's suddenly possible to create this gigantic object. By the way, if bending momentum is applied, we can get some stress by integration, and we can analyze how fracture happens here. And it can also put into the interactive design system. Here, I want to design a chair that does not collapse under some certain weight. So we have designed this furniture design system that makes something out of cross-section, sectional shape. But the problem is, it's very difficult to get the intuition where to break and how to make a strong shape. And our cross-sectional analysis can used here and can be interactive. The user design this object, it can provide a real-time feedback as this. And here is a design of a glass water holder using our cross-section analysis. So here, the simulation predicts it's a weak design, and it's get toppled or bended. But if simulation say it's okay, it doesn't go messy. Okay, let's go back to going to the final approach, but it's a data-driven approach for aerodynamic design. So I do this kind of aerodynamic design because I think a flying object is very, very cool. But the problem is designing flying object is very difficult. Sometimes we need to build a massive wind tunnel to analyze how objects perform under the currency. So our data-driven approach make this possible. And here is a project about airplane design. So the motivation is a computer-aided free-form airplane design. The user design airplane shape with this computer, and then we can fabricate and fly it easily. And here I want to demonstrate our airplane design system. So this is our airplane design system. So here we show some airplane, and also at the bottom it shows trajectory, how it flies. User can change the dimension of the object. Like here, I'm changing the position of the wing, and then this flight trajectory changes interactively. User can also sketch the shape of the airplane as like this. Okay, and it's a little bit difficult to make a flyable airplane with an interactive approach. So this one, there is a special function. Maybe it's due to the resolution of the monitor, it's very difficult to show the demonstration here. Actually, there is a hidden button. So let me instead show some video. So this is a design system we built. A user can sketch the shape of the wing and interactively see the flight trajectory while editing. And what's nice is there is an optimization function called make it fly. So optimization is running concurrently while user design. So user can just care about the design, overall design, and without thinking about how it performs. It's just focusing on the aesthetic part. And after the shape of the airplane is designed, we can connect this software to laser cutter, and we can cut it out, and we can easily assemble airplane by hand. And here is an airplane we built. It's a flying armadillo. And there is a launcher, and it flies extremely well. This is armadillo. It's not the airplane. It's surprising, yeah? And this is a view from back. And it's fly. And let me demonstrate actual flying armadillo. And here we are, the flying this shape, and fly this way. Thank you. So for this airplane design system, it's very difficult to actually simulate analytical fluid around the wind. because we have to solve Navier-Stokes equation with high-resolution mesh. And instead, I resort to using measured data. What we did is we built a 20 different airplane design, and we flied a lot, like 100 times in total, and then collect the flight trajectory and doing a machine learning. What's the shape of the wing result in the flight this trajectory? And with this data, we can handle any kind of freeform wing shape. And here is more example with a twin boom airplane. And this is a Stanford Dragon airplane. Okay, we also did a user study, and the left column is the airplane design without our system, and right column is design with our system. As you can see, many of the airplane with our system fly, although its design is more eccentric than the system with the airplane without our system. So along this line, we recently did a kite design system. It's due to the parent issue, I cannot talk very much about this project, but what we actually did is we want to design free-form 3D kite, not symmetric, but asymmetric, that can actually fly in the air very well. And that the challenge is how to model this aerodynamical force on the 3D free-form design. And it will be presented as SIGGRAPH, so yeah, please wait a moment. Yeah, and I want to show, just want to show how bunny fly with our system. So this is actually the bunny kite, Stanford bunny kite we built with our system. This is a lot of nonlinear, like NPR here, but this is bunny. Oh, okay. And it's flying okay, although it's raining very hard. Okay. So here is summary. So I'm afraid that I'm from mechanical engineering department when I was doing master on undergrad. But I was very concerned about recent design or mechanical design. There is an airplane from two different rival companies, but it's very similar, and it's boring year by year. In the early stage of airplane development, there is a ton of very nice and unique design, although they are not very functional, and it's die out. But it's more beautiful, and I think. Same as the car. This is a lineup, new car lineup, sedan lineup last year. As you see, there is 6 different companies make the almost identical car. It's hard to differentiate. But in the early development of car, there is a lot of nicer, much expressive design of car. And so the problem is the design system is, I think, too much care about optimal spec, not originality. And so that design get more care about optimal performance, not creative design. And also, I think in the design of functional object, we tend to forget about importance of interaction. For example, if we design, some people knit a sweater by themselves. Other way of spending time is terrible because people can buy sweater very cheaply. But while doing this kind of knitting, people can get more and more affected, get the emotional affection to the object. And also, it's this kind of interaction with this physical material is enjoyable for many people. So I think the future designs and simulation software for functional objects should more respect originality and interaction so that people can allow more trial and error to explore their original design. So as a conclusion, I have a lot of several research about some combining simulation and design. And these are combination of mechanical engineering, numerical method, and also interaction technique too. And I believe there is a lot of room still to explore. Thank you.